Hi, this is Computational Molecular Science Online, and I'm Professor Zygmunt. Today what I'd like to do is go through a very brief review of potential energy diagrams, and then do an example that's very similar to some of the homework problems that are on the first assignment. First of all, let's just do a very simple schematic drawing of the potential energy of a two-atom system, these two atoms that could form a molecule. So we'll be plotting potential energy on the vertical axis versus the separation distance between the atoms, or I suppose between two molecules, on the horizontal axis. And so our model, our simple model of a molecule, is that of two masses connected by a spring of some kind. And at any given instant in time, the separation distance between the two masses, or the two atoms, is this interatomic distance r. So what we find is that in general these two atoms want to sit at an equilibrium position, which is a position of minimum potential energy. And schematically what the potential energy curve looks like is something like this. And it turns out to be true for a wide variety of atomic and intermolecular systems, whether these two masses are atoms or whether they represent two different molecules that are somehow bound together. So what we see in this sketch is that there's a minimum value of the potential energy, and that corresponds to the equilibrium atomic distance. Sometimes we call that the bond distance when the bond is formed. Now, to the right of that, for interatomic distances greater than the equilibrium distance, we can see that the potential energy is attractive. It represents an attractive interaction, whereas for distances less than the equilibrium distance, we can see that it's repulsive. Now, how do I know that? Just by looking at the potential energy diagram. Well, imagine that this is some kind of a track and that we have a marble that can roll back and forth along the track. If that marble were going to sit at the minimum energy, it would be exactly at the bottom of the track. But if I give it a push to the right so that it's at a larger distance than this equilibrium position, then it will roll back under the influence of gravity. And this potential energy diagram doesn't just have to refer to gravity. It could refer to the potential energy of interaction between the two atoms and between their nuclei and their electrons. So we can see that if they're separated further than the equilibrium distance, they will tend to lower their potential energy by going to a shorter distance, and that represents an attractive force. Likewise, if they're closer together than the equilibrium distance, then they want to lower their potential energy by moving further apart, and that's a repulsive interaction. Okay, so that's what we can tell qualitatively just from this graph of the potential energy function. And let me do an example based on a function that's not the same as the ones I've given you on the homework assignment, but very similar. So let's just imagine, it might not be all that realistic, but let's imagine that we have a reason to think that this potential energy function could be represented by the sum of a repulsive term and an attractive term. And in this case, we see the negative term is the attractive term. That has the b over r. And the first term, the a over r squared, that's the repulsive term. And how do I know that? Once again, well, I just have to think about what happens to these two terms as the r value gets big or small. So let's look at the r value getting very small. If the r value gets very small, the first term is positive and it gets very big. And because of the r squared dependence, it's larger in magnitude than the second term. So the second term is a negative term. The first term will actually be larger and more positive. And that's this very sharp rise in the potential energy function as r gets small. That's due to the first term, which is the repulsive term. Then if we get to really, really large distances r, far beyond the equilibrium position, well, 1 over r squared gets very, very small, faster than 1 over r. So the first term is negligible compared to the second term, and the second term for large values of r is negative, and as r gets smaller, it gets more negative, and so it falls down toward the equilibrium position. So this is a sample potential energy function that at least qualitatively shows both the repulsive and the attractive term. So let's use this potential energy function to find an expression for the equilibrium position. And what's the criterion? Well, we can see that that's a minimum in the potential energy. And so what we want to do in order to find the minimum of a function, the same thing we would do to find a maximum, we take the derivative and set it equal to 0. That's what we want to do here. And then solve for the r value that makes that true. So the very first thing is just take the derivative of this expression. So d by dr means take the derivative with respect to r. So capital R here is a variable. A and b are constants. So we're just going to take them as being givens. We don't need to know the numerical values. We'll just leave them as a and b. So we take d by dr, the derivative of the first term minus the second term. And I'm going to write them like this because I find it easier to take derivatives when I have fractions involved to write a over r squared as a times r to the minus 2. It means the same thing, right? Minus b times r to the minus 1. Because my memory of the rules for taking derivatives, it's easier for me to remember them if I write them like this. So just remember a simple exponent here, a power of a variable. The exponent comes down when you take the derivative, and so this first term will be a negative 2 times a times r, and then the exponent decreases by 1. So instead of negative 2, it's negative 3. And that's the derivative of this first term with respect to r. The a is a constant, so it just stays there. Now the second term will have a minus, and what we've got, since the power in this second term is negative 1, there's a minus sign, but then there's a negative 1 that comes down, and we have the b, and we have r to the negative 2. All right, so that's the derivative, and we want to clean that up and set that equal to 0 to find the equilibrium position. So let's do that. What do we have here? We have negative 2a, and here I'm going to write it over r cubed. I'm going to revert back to the fractional notation. And then we've got plus b over r squared equals 0. And if I then just do a little bit of rearranging, add the negative term to both sides, I get b over r squared equals 2a over r cubed. And when I solve for r from this, I'm going to get the result that the r value that makes this condition true is equal to, let's see, 2a over b. And this is, therefore, the equilibrium interatomic distance. It's the expression for the equilibrium distance. And so that doesn't give me a numerical value, but if I knew the numerical values of a and b, I could plug them in and find this. So that's what I can get from this simple model. But that's not all. That's not the only thing I might want to do. What if I want to find the force constant? And you'll see in the reading that the force constant, when you have a potential energy function like this, is the second derivative of the potential energy function evaluated at the equilibrium distance. So what about what our book calls K sub s? So let's take just a minute to find out the value of that. We know that that's equal to the second derivative of u with respect to r squared, evaluated. What this vertical line means, we're going to evaluate that at r equals req. All right, so it's really not that hard of a thing to do. We've already taken the first derivative, so we just need to take the second derivative one more time. The first derivative is right over here. All right, so what I'm going to do, since the first derivative is this quantity in my box, that's du dr, I'm just going to take the derivative of that with respect to r. So here goes. I'll write it down like this. D by dr of negative 2a r to the minus 3 plus, since I've got the two negatives, I might as well combine them, plus b r to the minus 2, right? This is just the second derivative, which is what I'm looking for if I want to find the force constant. Okay, so let's go ahead and take that derivative. let's see, the negative 3 will come down, so I have negative 2 times negative 3 times a r to the minus 4. The second term, I bring down a negative 2 from the exponent times b times r to the minus 3. This is my second derivative. So I'll clean this up just a little bit and then plug in the value for Req, because the force constant is this second derivative when we plug in R equals Req. So first of all, negative 2 times negative 3 is 6. So this is 6a r to the minus 4. And then the second term is minus 2b r to the minus 3. Once again, at this point, I'm going to go ahead and write it back in the form of fractions. So it's 6a over r to the fourth minus 2b over r cubed. So now I'm going to plug in 2a over b for r. All right, so now what I'll be evaluating, I'll be taking du, d squared u, dr squared, evaluated at this equilibrium separation. Let me go over and scroll down just a little bit here, give myself a little bit more room. And that is what the force constant is. So here it's just a little bit of algebra. So I've got 6a over r to the fourth. So it's 2a over b all to the fourth power minus 2b over 2a over b to the third power. Okay, now I'm just going to cut to the chase here, because what I get with this first term, when I take the fraction in the denominator and flip it over and put it in the numerator, I end up with 6a b to the fourth over 16, and I have a to the fourth in the denominator. One of those factors of a is going to cancel in just a minute. The second term will be, let's see, I've got 2b times b cubed, because that comes up from the denominator, 2b times b cubed over 8a cubed. Wow, what happens here? Well, the a cubed in the second term stays the same. B times b cubed is b to the fourth. The 6 over 16 becomes 3/8. So this is actually 3 b to the fourth over 8a cubed minus 2b to the fourth over 8a cubed, and then can just finish this off right here, because 3 minus 2 is 1, so this is just b to the fourth over 8a cubed. And that is the expression for my force constant for this particular potential energy. So let's just review. What did we do? We started with a potential energy function that was given, that someone said, hey, this might just present a good approximation to the way a physical system might behave. Then we took the first derivative and set it equal to 0. That gave us an expression for the equilibrium position, Req. Then we went back and took the second derivative, evaluated it at the equilibrium distance, and found this expression here in the bottom right for the force constant. So that's very similar to what I've asked you to do for several different kinds of potential energy functions on the homework, and I hope this helps make that task a little bit easier. See you next time.